Fire requires oxygen. By all normal standards, striking a bright chemical flare and plunging it deep underneath the surface of a water tank should extinguish it instantly. And solid metals don't typically behave like organic tissue, rhythmically pulsing and contracting inside a dish of acid like a beating silver heart. Even a mundane pad of steel wool typically doesn't catch fire, but introduce the right catalyst and it erupts into a blinding white-hot inferno. These events look like glitches in reality, but they are precisely engineered manipulations of matter. Every impossible reaction we've seen is governed by one specific boundary, the categorical divide between metals and nonmetals on the periodic table. Metals typically hold 1 to 3 electrons in their outermost shell, which they readily eject. This makes them reducing agents. Nonmetals, meanwhile, absorb those stray electrons to complete their own outer shells, acting as oxidizing agents. Then there are the rule breakers. Mercury is the only pure metal that exists as a liquid at room temperature. That metallic heartbeat we saw earlier is a trick of electrical charge. When the liquid mercury touches an iron nail in an acid bath, it gains negative charge, causing its surface tension to spike and the drop to contract. It pulls away from the nail, loses the charge, relaxes, and spreads out again, creating a continuous mechanical pulse. If you want mercury to behave like a normal solid metal, you have to strip away its thermal energy. Drop it into liquid nitrogen at -196 degrees Celsius, and its atoms lock into a rigid, solid crystalline structure. An element's physical state is a mechanical outcome. It is entirely dictated by electron behavior and thermal energy. That blindingly bright burning steel wool operates on the same logic. What looks like traditional fire is actually hyper-accelerated rusting. By mixing the steel with hydrogen peroxide, we isolate pure oxygen gas and supercharge the oxidation process. Which brings us back to the underwater magnesium flare. Atmospheric air is usually an absolute requirement for combustion. Submerge a flame in water and you remove the oxygen. But if you pack a powdered oxidizer, a non-metal chemical that supplies its own internal oxygen, inside the flare itself, you bypass the water entirely. The chemical reaction feeds itself. By mastering the exact chemical requirements of combustion, we can construct reactions that completely ignore the constraints of their physical environments. This pie chart shows the percentage breakdown of gases in the air. It perfectly exemplifies a chemical mixture. As seen in these distinct slices, even though nitrogen, oxygen, and trace gases blend together, every element retains its original chemical properties. Compounds operate differently. When elements chemically bond, they permanently trade or share their valence electrons, creating an entirely new substance with a completely different set of physical properties. Understanding how these bonds form allows us to actively manipulate matter. We can chemically bond oxygen to aluminum to anodize and colorize metals, or we can use electrical currents to electroplate dissolved loose nickel ions into a pristine, solid metallic layer. The boundary between a loose mixture and a chemically bonded compound is the exact threshold where passive observation turns into active engineering. This mastery scales up to massive engineering feats. Hydrogen is a simple non-metal, but when we burn liquid hydrogen with liquid oxygen, it creates a violent 5,500-degree Fahrenheit reaction, providing the thrust needed to push heavy rockets out of Earth's atmosphere. We can also tame that same reaction for precision power. Hydrogen fuel cells safely generate electricity for public transit systems, like this bus, which emits nothing but plain water as its exhaust. Helium plays a different role. It is generated from the radioactive decay of heavy elements deep underground. Because its electron shell is completely full, it refuses to chemically bond with anything else. That exact inert nature makes it invaluable for extreme physics. We exploit liquid helium's uniquely low temperatures to supercool the massive curving line of superconducting electromagnets inside the Large Hadron Collider. The periodic table provides the specific chemical parameters required to command the building blocks of reality. Mastering these entries allows us to engineer the modern world.